Hey, ChemStars, this is Mrs. Vandeloy bringing you section 1.3, Elements and Compounds. We will begin this discussion just talking about the elements, all right? So we can look at the periodic table of the elements, all right, and divide it up into metals, nonmetals, and metalloids. So we're going to just do an intro, in a sense, to those properties. In chapter 5, we'll spend a whole lot more time talking about this, all right? So we're going to talk about a periodic table, metals, nonmetals, and metalloids, okay? So let's take a look at this periodic table. First of all, what do you notice? Look at the title right here, the periodic table, the names of the elements. Every single thing in here are your elements. It can be found in a larger periodic table in the back cover of your book. You're going to have your own copy of it, and if I were you, I would get it out right now and maybe take a look at it, especially for the next couple pages. But in the meantime, we can look at the periodic table that I put right here for you. And I'm going to scroll down a little bit more and try to get the whole thing in here. And you're going to see it's kind of organized in this kind of fashion. And if you look at the key here, the red is the metals, the kind of the green is the metalloids, and the, I don't know, orange color is your metalloids, okay? So we organize this, all right, in two ways, okay? The periodic table is organized by the vertical columns and the horizontal columns, okay? So if you look at it, the vertical columns, vertical goes up and down, right? We call those groups or families, and horizontal goes across. So for example, let's kind of do this. We can look at here. This is going to be what? This is a group or a family. So we'd call this group 1. So everything in the first column is group 1. All right. Well, what about the next one? That is group 2. Okay. And if you count over, do you see this? Group 1, group 2 goes all the way over here. And oh, look at helium. Look above helium. That's group 18. So there are 18 groups or families in the periodic table, all right? And why do you think they call them families? Well, there are similarities, all right? I know if I've taught some of your brothers or sisters, there is similarities that run in your family. You're not identical, but you have similar eye color or similar, nose or something like that. And that's the same way with the families here. That's why they call them that there is some similarities with all the elements in group 1. There's similarities in all the elements in group 2. There's similarities in all the elements in group 18. Okay, well, what about the horizontal rows? What do I call these? I call them periods, all right? So over here, let's just pick one. Let's go, this looks like a good one. So here I have, this is a period, and it's actually a period, well, this would be, oops, sorry about that. This is period 1, period 2, period 3, period 4. All right, so I'll just leave it at period 4, okay? And there's not really a lot in common. If you notice, you start with potassium, these are metals, and you have some metalloids, and you have some nonmetals. There's not a whole lot of similarity between, let's say, potassium and bromine. All right, you really can't say that. We're going to talk about in chapter 5, the thing they have the most common is really about the size of the atom, and even that differs, but that's the only thing they really have in common, okay? So, but that's still called a period, okay? We'll talk more about that. And if you count, ready? So period 1, 2, 3, 4, 5, 6, 7. Well, what about these guys down at the bottom here? Well, cerium starts period 6 and thorium starts period 7, all right? If you look, here is lanthanum, that's number 57, cerium is 58, actinium is, I can't read it very well, 89, and thorium is number 90. So if you could expand this periodic table, they'd fit right in here, okay? So this is still period 6, and this is still period 7, okay? So there's a total of 7 periods, okay? What I would like you to do next is on this periodic table, I want you to draw a staircase, okay? Why don't you go ahead and do that right now, and it goes right here, okay? So start with the edge of boron and kind of do some like this. And what this staircase does, in a sense, is separates the metals and the nonmetals. And if you look closely at the color on this periodic table that I have, that orange is your boundary, okay? And that orange is your metalloids, and they have properties of either metals or nonmetals, okay? So what happens here is that we have, hang on a second. All right, so let's scroll down here. So where are your metals found? I go left of the staircase. Okay, that's what the line you drew there. The non-metals are the right of the staircase. The metalloids in general are on the staircase. I notice there's some major exceptions. Look at aluminum. It is not a metalloid. It is not orange. It is not. It is clearly a metal. Think about everything that aluminum is. It's the properties of a metal. All right. Well, what are some of those properties of a metal? Well, let's find out. Oh, by the way, here's some examples. Aluminum, remember I put them there for a reason. Magnesium, we've already seen magnesium. You're all familiar with copper and silver. Those are examples of your metals. Some non-metals would be carbon and oxygen, neon. Neon light is a gas. Your metalloids are the ones on the staircase. I'm doubting if you've ever even seen silicon, germanium, or arsenic. I hope you haven't seen arsenic. It's not a good thing to have, all right? But those are your metalloids. Your properties of your metals, they're shiny. Remember that magnesium? Conducts heat and electricity, just like aluminum or copper wiring does. Malleable, you can bend it. Remember how I bent that magnesium wire before I burnt it for you? All right, that means malleable. Carbon, in its elemental state is dull. It's like your charcoal briquette, not your diamond. All right, that's a special case of carbon, but your charcoal is a more common form of carbon, if you will, is dull. Or there's no shine to it. Oxygen and don't have any shine. They don't have any, texture like that. Carbon, oxygen, neon, they don't conduct. Now, I should say there's a different special form of carbon that does called graphene. It does, or graphite, it does conduct, all right? Well, just know that graphite does conduct, but that's a special case. It's brittle, all right? If it's a solid form, it's brittle. So like that charcoal briquette will just fall apart in your hand. Sulfur, I don't know if you've ever seen sulfur, it will fall apart in your hand, okay? And a metalloid can have properties of either. So silicon can be shiny, it can conduct, but it's brittle, all right? So they have properties of both, okay? Okay, so this is your last page, your notes. We're getting there, and if you haven't done so already, I would get out your own periodic table, the one that you're given in class already. Why? Because it has the symbols and the names and the numbers on there, so you have a reference to look at. So when I am referring you to a certain element, you can look at it yourself, okay? And like I said, notice it's called the periodic table of elements. These are all the elements known. Right now we have 118 known elements. Okay, so if you look at the periodic table on the prior page, it's not complete. They have discovered and named and verified all up to 118. All right. And I don't know, I've been doing this for a long time. All right. But it still amazes me that everything that we know of is made up of either just those 118 elements or combinations of those 118 elements. Every single thing that is matter is made up of 118 different elements. It's crazy to think about, okay? Well, anyway, so let's kind of start from the beginning. Elements, again, is the simplest form of matter that has a unique set of properties. If you go back, like in the 1600s, alchemy was a big deal. And what alchemists were trying to do is turn base metals into gold and to get money, all right? What they were actually doing is swindling people. They were not making gold, they were making, brass, okay? That looks like gold. But the most people didn't know that, and once they found out, the alchemists would probably run out of town, okay? And the whole idea of this is they wanted it to be a secret. They wanted their recipe to make, quote, gold, which is brass, a secret. So they use these symbols that most people didn't know what it was. And therefore, if they have it written down, their recipe, no one could read it and reproduce it, okay? So what are these symbols? Well, you might recognize some of them today. So this is gold. It's supposed to represent the sun. It kind of makes sense, doesn't it? So that's why it's a circle. It's perfection. A circle is perfection, okay? Well, this looks like the moon. Well, that was, oops, the common symbol for silver, okay? And that makes sense. The moon, if you look at it at nighttime, looks kind of silvery, doesn't it? Okay. Well, the next two I think are kind of interesting. All right. This, if you recognize that, is a symbol for woman, isn't it? Well, it's also the symbol for copper. And back in those times, mirrors, silver was very expensive and hard to get to. Copper was a little bit easier, so they actually had mirrors made out of copper. That's what it's supposed to look like. Here's the handle, here's the mirrors, and apparently ladies like to look in the mirror a lot, all right? So that's your symbol for copper. Now you might recognize this as a symbol for man, for males, and that is your iron, okay? This is a shield with the spear. Isn't that a manly thing to do? Go to war and fight with your spear and your shield there. Well, guess what they're made out of? They're made of iron. So I call it the Iron Age. So there's that. This one I think is kind of interesting. If I were to draw it, it comes out a little bit different, but that's the basic look of it. That's lead. And it's supposed to represent a slow moving snake. All right, believe it or not, this is a snake. Here's the tail. I don't know. See, when I make it, there's not a line here. And this is the head of the snake right up here. And that's your lead. Lead is a very dense, a very, thick metal, very slow moving. All right, I didn't make this up. The last one is actually mercury. And it kind of looks like that mirror again, but it's not supposed to. It kind of looks like the devil. All right, those are the devil horns. And if you think about it, mercury, what you know about mercury, it's a liquid, isn't it? Liquid metal. It's the only one that's a liquid. And it was an element of mystery because it was this liquid thing. And being mysterious, they thought it was like from the devil in a sense. So that's why it looks like a devil. But that's your mercury. And so instead of using these, wouldn't it be really complicated to memorize all these symbols? Holy cow, all right. Well, you can thank the Swedish chemist Jan Jacob Berzelius, all right? It's not John Jacob Jimmerheimer Schmidt, it was John Jacob Berzelius, all right? He's a Swedish chemist. He was a professor up in Sweden, I don't know what college, in the early 1800s. And he was considered like the foremost chemist of his time, all right? One of the earliest well-known scientists. And he got kind of tired of all these symbols. He says, I want to make it easier. And it's kind of interesting to look at the history of this. Is Lavoisier from France a little bit earlier in the late 1700s had come up with his own method of naming elements because Lavoisier was also tired of using all these symbols. But Lavoisier renamed everything in French, all right? So Berzelius from Sweden, his colleague says, oh, let's make these Swedish names. And Berzelius said, no, I want to use Latin. Latin because it's more of a universal language, all right? A lot of people learned Latin back in those days. So he's the first one that came up with the idea that let's use the first letter or the first two letters of the name, and that's how they're going to identify them. And he did a whole lot more, but I'll just leave it as that. I'll give you another history lesson another time if you really want. But you can thank him for getting away from all these. So carbon, which is not Latin, so we've expanded from it from then, would be C. Well, C has been used. So if I want calcium, now it's Ca. Well, what about cobalt? It's Cl. All right. So if the initial letter was already taken, then say, okay, let's take the first two elements or the first two names. So that would be true for there. I can do hydrogen, and it was discovered before helium. All right. And so because H was used, and we have He. Okay. So we can again thank Berzelius for helping us out there. Okay. I find this part fascinating. Maybe this is a pet, a hobby of mine is researching these elements and how they come to be. I could talk for a long time, but I'll try to keep it short. Most of them are named for people. Usually the last 20, the newest elements. So Einsteinium, Fermi is a FM. Mendelevium is the one that came up with the periodic table. Nobelium, Alfred Nobel. Rutherfordium. Number 96 is curium from Marie Curie. Number 109, I think is fascinating, is meitnerium. That was from Lisa Meitner, who actually proved Albert Einstein wrong. Okay. We have them named for places. Francium is number 87. Germanium. Now, these are like planets, uranium, neptunium, plutonium. This is americium for America. Berkelium and Californium. This is the lab, the University of California Berkeley lab is where a lot of these large, big elements were actually created. All right, so that's where those came from. I threw Curium up here because it goes 92, 93, 94. Where did number 96 go? Oh, that was Marie Curie. And then there's properties. There's some great stories here. Here we have number 53 is iodine, is from the Greek iodos, which means purple. My battery's running low. Hang on. Well, in case you're worried, my battery's not plugged in, all right? So I can continue on. Lucky you. I'm almost done, though. All right, and then we have, oh, I didn't tie these. All right, so iodos is violet, and iodine is a violet nonmetal. Cobalt is actually German. That means little devil, because it's very, very difficult to separate cobalt from nickel, which is the next neighbors. Number 28 is nickel. I love this story about antimony. See, it's SB. Well, I could go down and talk about its Greek or Latin name. It was originally called stibnium. That's where it's SB. And the story goes, and this is a true story, by the way, that a French monk was in charge, or lived in a monastery. They're very self-sufficient. There's a monk that's responsible for growing the garden. There's a monk responsible for cleaning the kitchen. Well, there was a monk who's responsible for feeding the animals. And this particular monk realized that when he fed the pigs the stibnite, that they got fat. And back in those days, it was a big deal to have some fat animals as more meat to eat later on. So he noticed that his fellow monk friend was a little bit skinny, so he gave him the same, stibnite. And what happened to that monk? He died. All right. So after that, it became antimony against the monk. So the monk died. They called it antimony, and that's why it's no longer stibnium. All right. So anyway, those are some properties. It's poisonous. The Greek or Latin names, I can finish this off pretty quick. Oh, let me do this real fast. There we go. And so gold, this is Berzelius again. He's the one that do it. Auric or Orium was your gold, AU. Argentinium or Argentinum is your silver. And believe it or not, that's how Argentina got its name. There's silver mines in Argentina. Lead is plumbum, and that's where the PB comes from. Helium is the Greek helios, which means the sun. And during a solar eclipse, they noticed that the spectrum of the sun had a new unknown lines, if you will, and so that was how helium was discovered. Cu again is copper for cuprium. Sn is stannous for your tin. These are all your Latin names. So this is where Berzelius was coming up with all these symbols there, is from the Latin. And I found this was kind of interesting. Here's Na is sodium. So where'd that come from? Well, Na is your Latin natrium. And what happens that they came up with soda from the sodium carbonate, which was used to make soda water, which is a headache medicine. So that's where that came from, but it came from the Latin natrium, and that's why it's now called sodium. Potassium is also very interesting. The Latin is kalium, and that's actually from an Arabic word, which was from like alkali, and which is why they're called alkali metals actually. But they realized that it came from the residue from pots or pot ash, and it became potassium. So that's where that came from. And you know what? I could go on, but I think you've had enough. No, you'll not be tested over where all these names came from. So trust me on that. But it's a little bit interesting on where some of this history came from. They're not just made up out of thin air. There was reasons behind it. So I will quit now. I went a little bit over. I'm sorry. But I'll just say, don't wait to be great, and look this over for your next flipped quiz. That's the end of chapter 1. We'll see you later.